Yeah, hi. So thanks a lot. I'm very pleased to give you today a short introduction, an overview over one of our main projects at the Fraunhofer IO in Stuttgart, which is called AutoML, so automated quantum machine learning techniques for industrial applications, and to give you an insight into what we are doing here currently, so state of the art for the industry in the scope of quantum and automated classical machine learning techniques. And yeah, as I guess I guess the pre-knowledge is not so much here into quantum technology. That's why I also wanted to give you a short motivation what is this doing. I'm pretty sure that you know this guy here on the right hand side whom was the inventor of gravitation maybe. I don't know if later Einstein maybe, but this guy has shown, okay, if you have an apple, it drops down. That's the classical world as we know it and where we can do a lot of things. On the other hand, I guess you also know this guy, especially his cat here, which lives there, is Schrödinger's cat. So below a certain length scale, the apple, so which drops down, ends in a cat more or less with dead alive at the same time, or the branch or down. And here we can use techniques which are very, very powerful for quantum machine learning, either on its own purpose or to improve classical machine learning techniques. And the idea is, can I use these? So in principle, three principles here on the left-hand side of this border, which is uncertainty, so Heisenberg, which is superposition, so Schrödinger's cat, or entanglement, which was the Nobel Prize last year given for. And we want to use these things with respect to applications in the real world. And be aware that this has been reached for several, fields like imaging, for example. You know it from NMR, CT, so medical imaging as positron and electron tomography as well. So the PET, which you know, and also recently the QKD, quantum key distributions, which you can have quantum safe channel for communication. Question is currently the state of the art. How can I use this now for computing to improve my current algorithms and software toolings with these kind of basic principles? So this will be the main talk of this, or purpose of this talk. How can I use this automated without knowing what I actually do? So explainable, but not by the end user. And what do we expect here? So we expect that if we use these techniques, we reach goals in real time instead of, things which are already solvable, but you can solve them faster. For example, you want to include traffic jam information into your logistics problem. So and not update your plan schedule every week, but say on real time. Or you want to do the runtime of an algorithm such that it is actually executable in anyway, not in lifetime. Like, for example, think of CFD calculations when you want to fluid dynamic questions which you want to simulate and don't use a 3D print and put it into a wind channel. We want to go sustainability is a big issue. We don't want to have big HPC power for algorithms and software toolings in the industry, but want to use quantum computers in the sense you only can simulate 70 qubits. Everything above you can't simulate with an entire farm. So, I mean, the latest IBM quantum computer is 433 qubits already. You cannot simulate it anymore. And we want to have a higher accuracy, not only fastness, but also accuracy is a big issue. But we don't want to understand it in detail as an end user and still reach these goals, so automated. And what are use cases we are actually tackling here in Fraunhofer? So there are different ones, either combinatorial optimization, maybe you heard all of it, in the sense of optimization, some kind of logistics problems, shop problems, so scheduling problems. But in the sense of machine learning, and the talk should be all about, it is more regression and category and classification tasks, as well as anomaly detection, which we want to use here this technology for. And if you do something with an industry, the pipeline is always the same. So you identify something, the problem, and reduce it to a proof of concepts which you can currently solve. Then you model together with the industry the system and transform it here to the chip, or write the algorithm, transform it to the chip. This is the German backend. So the IBM chip in Germany deployed in Eningen, 72 qubits, run the algorithm, post-process it, and deploy it in the company. So this, and how does a POC look like? Only that you get a feeling of quantum computing. If you have an n cross n Sudoku, better solve a 2 cross 2 Sudoku first. And if you understand this, you can solve everything. And that's more or less the same with logistic use case, as I said, a small route or a small regression task. I mean, here we know the outcome, but there's an algorithm out there searching through unstructured databases, which has a runtime improvement of square root. So it's quadratically faster. It's called Grover. And then you write an algorithm in a Python bibliothèque, and then you execute it and get back a probability distribution. So with the highest probability at the correct solution of your Sudoku. And this is extremely powerful. So this is exactly what we want to do now with use cases. Reduce them, solve them, and get with the highest probability from the quantum computer the correct solutions. And yeah, that's the idea of this AutoQML, automated quantum machine learning, which we here from the quantum side, both Stuttgart Institutes, the IAO and the IPA, drive here with our quantum background. And then we tackle 4 use cases here from the applicants, so from Zeppelin, from Trumpf, from the IAV, and from the KEB. And the same in the sense of we want to spread it in the end, we want to have a multiplication. So that's why we also have the USU and the GFT as software developers making an app out of this that you can use this also for different use cases. So we chase new solutions, we chase increased performance, and also simplified migration such that you don't need it in the end in the sense of AutoML. And as I'm pretty sure that maybe not everybody knows AutoML, let me also say what this is all about. So here we have the 4 use cases. It's all about anomaly detection and image data in the laser cutting process. It's error prediction for transport systems, self-driving transport systems. You want to omit crashes. And it's digital twins. You want to simulate how the automotive behaves, and also price prediction tasks for rental services. And all these use cases, regression and classification tasks, usually you solve currently with a data and domain scientist by running the entire machine learning pipeline from the data set till the feature selection, the modeling, and then the prediction. Therefore, you need both experts, and experts are rare. So what are people currently doing here is the entire pipeline. So, and there is something in the machine learning pipeline called cache. Has nothing to do with money. It's a combined algorithm and search selection and hyperparameter optimization. So you have a bibliography with a lot of ML algorithms, with a lot of them, everyone coming with its own hyperparameter. Usually the expert needs to optimize all of that, search the best algorithm, optimize its input parameters, and then run it. That needs a lot of knowledge. AutoML optimizes the entire thing, so the search for the best one and its hyperparameter adjustment. And there are different AutoML algorithms out there, like for example AutoSKlearn, maybe you heard of sklearn, which does this, or random forest is one of the bibliothèques, which also is an AutoSKlearn. So every of these frameworks has a lot of ML algorithms inside, which you search through with a grid search usually, and then optimize it. But this is done now all behind a certain black box, or in a certain black box. You don't need to take care. But this costs a lot of resources, so you need HPC for this usually, and that's why we come now with quantum and say, okay, can we use the power of a quantum computer in the same sense of unstructured database searches to improve this performance of automated machine learning? And how do we now improve this with quantum machine learning? We add to this classical, so random forest, neural networks, CNNs, we add here new methods like quantum kernel methods, like quantum neural networks. At the same time, we also use quantum computing to improve the hyperparameters of classical machine learning routines via quantum search algorithms, such that you get in a hybrid way the best out of 2 worlds, so the apple and the cat combined more or less. So and that's then the pipeline, which everything should be hidden, because in the end this needs a lot of knowledge. Now you also need quantum computing knowledge, but maybe you don't have this in your company. And only to give you a hint how this looks like currently classically, these 4 lines is everything you need, really, for applying machine learning to your use case here. So you import here a framework which is called AutoQlearn. It's one of the latest ones by Google. and then you just run it. You just make the fit and the prediction. And the same thing should now work for including all these quantum techniques. So nobody here applying this should need to know quantum technology. And I brought you 2 use cases to give you here some kind of a feeling how this looks like. So one of the use cases is from Zeppelin here. You maybe know these initial Zeppelins, right? But they also have a big Caterpillar rental services and so on. So they are very much interested in how is the price of a Caterpillar machine progressing over time, or also I give you a certain machine and tell me the price for it. So a regression task. And this is a lot of value for them if there would be an app which does this automatically without implementing here too much manually. So we search through data, or here at Zeppelin, the expert is also around. It's too blending. It's Horst Stühler, will be also maybe around our booth. So we search through the internet, through the databases, and collect a lot of data, public data available of all these brands, models, series, extensions, and so on. And then we want to predict the price. So we train, first of all, different classical machine learning methods and automated machine learning methods to predict the price of these machines, on train it with these data sets. And what we found out here, and this paper has already been published here, is that actually you see that the AutoML method, for example, AutoGlow, and this was exactly the 4 lines which we have seen before, has the best, or performs the best here on the left-hand side, even better than the manual ML pipelines. And also needs the less runtime, so it has the best runtime, so it also performs the best. So actually, you don't need here the expert in general, so your machine learning expert to solve this kind of use case if you use these techniques. So far, there's no quantum in. This is all classical. So the next thing in this project together with Zeppelin, he's here to not only benchmark and compare AutoML techniques with classical benchmark lines, but also to use quantum techniques. And I don't want to go into very deep details of quantum. I only want to give you a short idea why this is so powerful. Think of data points in a circle and outside a circle, and you want to classify them, and it's usually done linearly. So if you have a circle, you cannot classify points inside and outside with a line, right? Doesn't work. If you add now the radial dimension, so the radial distance of the circle to the third dimension, then immediately everything which is inside the circle is, say, close to the bottom, and everything which is outside is above. And then I can just put a plane and classify it linearly. And exactly the same is working in kernel methods, which we do classically with so-called support vector machines, for example. But a quantum kernel does exactly the same. It takes its data, more or less, which you see here, on the left-hand side, and then loads the data in a quantum circuit. This is how it looks like. And you're then directly in this extremely large Hilbert space of Schrödinger's cats. Hard to understand, but you have everything possible. That gives you directly an overfitting because it's so powerful that every point is its own class. So then we project it somehow, opening Schrödinger's box, and we project some things. This is maybe too complicated, but the key message is that quantum computing in general has very powerful prediction schemes. And this we run then in Eningen and exactly solve the same use cases, including it in this framework that you can use it without prior knowledge. Yeah, and the second use case which we solved here, and I wanted to show you, is image for anomaly detection, image data. So together with the company Trumpf, I'm also sure that a lot of people know this company. So they have laser cutting of sheets, metal sheets, and these here you see such a machine. There are certain bars underneath, and then the plate is on top and is cut by a laser head. The problem is if the sheet is somehow bad on this plate, and then it happened that the blade tilts. That's very bad, because if the plate is tilted and the laser head can get easily broken if he hits the tilted plate. So the idea is, okay, I should have a camera on top which detects if I have more or less a bar underneath my plate that the plate tilts. And then it says to the head, okay, stop, because otherwise you get broken. So it's an image task, but this is very tough because you have a lot of effects in these image data, like for example, different colors, surface texture, and so on, different angles. It's a very hard task to train. So Trumpf built a synthetic data pipeline to generate a lot of our training data here for our algorithms, and we solved it first with a classical CNN. And here you see such a spar again here, and you have these different bars are then translational invariants, but you have them here, and then you have here a bad resolution because you're tilted in your camera on top. You train this by saying, okay, here I see such a bar. This is then feed it into the CNN. Here I have it, and here I have it, and then you train it, and this gives you 1. And if there's no bar, then it gives you a 0. So you get a bit string more or less for the entire bar distribution. And this bit string is then learned by the CNN and gives, if the head is over such a 0, a stub criteria. And the same thing we solve now with quantum techniques, only that we train this now by a quantum convolutional neural network. And I brought this to give you an insight, what's the state of the art. Currently you have seen that we have 27 qubits in Ening, which is not so big, right? This is a small one. But here's a technique out there called quantum classical convolutional neural networks. And if I have an n cross n image, or I don't know, 250 cross 250 image points, then I can, with an raster technology, always go with 4 image points with an encoding here to this, against quantum circuit, use this kind of what we had in the beginning, entanglement, so this Nobel Prize stuff there, and the Schrödinger cat, to find a very powerful operation, feeding it back to the classical feature map, and then get a better result than it is with a classical CNN. This can already, so due to the amount of qubits, can already be done today. And you can only do it either in the convolutional or on the right-hand side also in the pooling layer. And study currently what's the best approach in terms of performance using these quantum techniques. And both, so the CNN comes then together with the QCNN in this AutoML framework, and in the end you use the same 4 lines of codes. And then behind of this, there's a decision characteristic which chooses you dependent on your data, and also dependent on the growth of the hardware, of the quantum hardware, for example. For these data, choose me this algorithm first and try this hardware first, because there are also a lot of quantum hardwares outside there, or also classical methods out there. So decision characteristics, performances, and so on is a very important topic here to provide a very powerful framework in the end for our end users. Okay, with this I hopefully have given you a nice insight into what is doable with automated machine learning, and also in combination with quantum machine learning techniques, and what can be used maybe though. In 1.5 years we end this project, hopefully by providing exactly these tools via quantum apps then in the end. Okay, if you're interested in how use cases can be solved, I also wanted to give you a short commercial or whatever. We just wrote an entire study where we solved logistics use case with the Schwartz group, with Kuma Vision, like these job shop problems and so on, which I introduced before if you're interested in how one can solve this. And also run currently an industry training program, which we ran last year for the first time and repeated this year. And last but not least, so if this is very interesting for you, we also built a quantum and AI experience center down in Ening at the IBM headquarters, where we exactly demonstrate these effects of quantum, but also of AI, virtual reality, which you can use to deep dive into these technologies, into the hardware, and get a feeling how to program both worlds here the best. So you're happily invited there if you want to join. With this, I thank the organizers. Hopefully generated some insights and some knowledge on your side. And thanks a lot for the attention. Thank you.
Thank you, Christian. We have time for questions. If anyone would like to ask questions, please raise your hand. At the back there.
Hello. With reference to your infrastructure, how many qubits can you work with?
So yeah, as I said, so the amount of qubits heavily depends on the hardware you have. So for EINS, for example, you need way less qubits than for superconducting hardware, as IBM is doing, or Rigetti or D-Wave. But essentially, so one can think in the terms of what you might heard of logical qubits. So this post-NISQ era, so the powerful quantum era where you can prove everything, so all these improvements, exponential speedups and so on, and therefore you need a lot of qubits, because you need to combine physical ones to logical ones, which are error-free, and then you need to calculate. This will still need some time, and this year, hopefully, IBM releases this 1,000 qubit system, and then it turns out higher and higher and higher and higher. So they double more or less the amount of qubits the last few years every year, but it's not that it's so. There are also algorithms out there which don't rely on that much qubits, as for example this quantum convolutional networks. So the question is always which application do I want to realize? How strong is the connection in your problem? So how much qubits need to talk to other qubits, more or less, because I also can classically parallelize on a quantum chip. This is also possible. Yeah, but the current state of the art is like that we are totally happy with this 27 qubit chip currently and don't need more than 27 all at the same time currently. But you can think of, okay, I want to make a classical parallelization, 27 here, 27 here, 27 here, and 27 here, and can run 4 times faster. So it works also. So we would be glad if there are more, but for purposes currently, if we are above 70, we have already this quantum advantage. So yeah, hopefully this answered a bit the question.
We have time maybe for one quick last question.
Hi, thank you very much for your presentation. It's very nice. I have a question on that regression problem that you mentioned on pricing of drugs, I think. You compared several classical automated machine learning schemes.
Mm-hmm. Yeah. Yeah.
And then next slide, you showed the quantum version of it, but you didn't mention how it compares to the other ones.
Yeah. Yeah, for a good reason. So far, it won't outperform the other ones.
There will be no break,
so that's the proof of concept version. So, but the question is conceptually, do we expect that this kind of feature method will outperform once we can scale up the system? So we are on currently, both developing this benchmark. When do we outperform? And from this also develop characteristics when to use which algorithm, because this exactly is the question. So this defines the decision characteristic in the framework, because you don't want to take care of it in the end. You want to use the 4 lines, right?
Okay, thank you so much. I guess we have no more time, but you're around, right, for the event, and
Exactly.
Fraunhofer has a stand, so you can also visit them there. Thank you so much, Christian.
Thanks a lot. Thank you.